So I will talk about orbital ordering, and as so late in the program, there will be a few things and repetitions of things you have encountered, but I hope there's also somewhat different perspective of some of the aspects that we've seen here. So no need for an introduction. Let me just again point out that the early work here by also Eduardo was that we have interaction-induced type of Pomeranchuk instabilities that then also entail all these spin transport phenomena. And we'll come back to this question of what is actually inducing the alpha-magnetism. But instead of an introduction, I want to come back to one of the minimal toy models, which is this TT prime U Hubbard model, which by now 2 years ago we started to look at as a really minimal model to model an alpha-magnet. And what we do here is we always start from a normal Hubbard model, TT prime, and then we just take a tunable parameter delta that just makes basically this slightly weaker, this slightly stronger, and then we can even go to delta equal to 1, which would tune us to the leap lattice and so on. Okay, so that was the simple model, and then we did something like a standard Hartrich-Fock type calculation, and you see this nice spin polarized band structure as expected. But we've seen lots and lots of materials in this conference, and it's really nice to see that there are so many candidates. In this work down here, we try to see whether solid state materials are the only platforms, or whether we can also go to other systems here, which are these called atomic systems, because there people have now worked for 2 decades to simulate the Hubbard model or the TT prime model. And so then the question is, since we know how to do the simple modification to go to our checkerboard Hubbard model, can we actually do that? And let me point out that this is a long-standing endeavor. Every few years you get another nice fancy paper for actually seeing just the Néel state in the Hubbard model. But the challenge is really to go to low temperatures. Okay, and so currently, you go down to temperatures which are roughly, a quarter. Maybe you can go a bit lower now. So you're, touching essentially the area where you would see the phase transition. But you can do small systems, and the main advantage is you can also now do real space detection with these quantum gas microscopes. So here you really see the up and down spin arrangement of the Néel state. And now the point is you can go to low temperatures, and you have relatively small system sizes where your thermal correlation length is larger than the system sizes, which means that you're basically probing an ordered state. Okay, and so the point is, then the question was, now how would we modify the setups to basically realize in cold atomic gases also some of these alpha magnets, and then we can study different things and use also these new real space detection probes, which are maybe not that natural in.
At what temperature is the star?
The star? Well, it's roughly it's a bit lower. Let me think how to go back. Is that? Doesn't want to go back here. This star here. I think it's roughly around this area. Yeah. I don't know the precise value, but you're getting in the area where, if you are in the really undoped case and so on, that you would see the transition temperature. Oh, you mean in terms of like actual talent? Oh yeah, in this system. Yeah, this is. Yeah. No. I mean here, yeah. This is compared to the bandwidth. Yeah.
I always joke that any high temperature superconductor is much colder than any equal atomic system in terms of the Fermi energy.
Yes, sure. Yeah. Yeah. But the key thing is really, if you're good enough with smaller systems, they reach now temperatures such that the thermal correlation length are large enough to basically treat it as an ordered state. Yeah. Good. But of course, that doesn't help you to see interesting criticality or something like that.
Still waiting for an answer to the problem, does the Hubbard model superconduct?
Yes. No, but they need to go a little bit.
They have to go quite a bit lower.
So we're doing.
Sorry, I always say that nature has a sign problem as well. Okay.
So we're doing something much simpler here. The question is just, you have these optical lattices, and then you work out essentially how do you get this checkerboard supermodulation pattern. So you just take another, so this would be the standard laser setup to get a square lattice. You know, that's the simple one you find in textbook. And now you take a second laser and you rotate it by 45 degrees with half the wavelength here, and then you form this checkerboard pattern, and then you solve the band structure in this continuum, and then you can see in the, you know, deep limit of the potential wells, you just, you know, directly see that you get your tight binding like model. So it works really well, and you know, you can just basically give a recipe to the people how to basically program the optical lattice there. So why would you like to do that? Well, first of all, it's nice to have a different platform to analyze it, and second, you can really now do things, for example, like looking at real space probe. So one thing that we looked at, for example, is you just have an excess particle density in the middle, and then you just basically let it go, and then you see here that now the upspin and downspin will spread in this diffusive form very anisotropically, just because you know from the Einstein relation, from the spin split conductivity here, we know that this transports also in the diffusion constant, and then we can basically get this spin asymmetric diffusion, and that would be like something that you could easily probe in these systems. Okay? And of course, if we could go even further down in temperatures, you know, that would be a nice area where we could, you know, look for exotic superconductivity and so on, what we all saw.
Because, like naively with this entropy increase, I would assume that the spin should be distributed equally, and here it looks like it would be concentrated in certain directions. So.
Yes, so here, I mean, you should think of this as really the transient dynamics and so on, yeah. So we are not, because there's also all things about the trapping potential and so on, but you can, you know, that's basically standard experiments, what they do, that you just have a trap, you take a particle imbalance, and then you change the trap potential, and then you see this, and you would directly see for transient times when they measure this asymmetry, yeah. Eventually, you're right, it will equilibrate. Good. Okay, but then here's the effective phase diagram, and then you saw we had this parameter delta, and you realize that there's actually no phase transition, yeah? So that maybe comes back to some of the discussions from Monday, is that we can start with a normal Néel state, the normal antiferromagnet, and just very smoothly go into our altomagnetic phase. And so then one question we try to think about is, you know, can we actually have something like a true phase transition, or is there some more interesting role that the interactions can play than just giving us, you know, like this up-down spin pattern? And that brings us, you know, to this other subsequent work that we looked at, that normally we get the spin anisotropic density imprinted from the crystal. That's why, you know, you look in all kinds of material databases for example, starting even, you know, if you want at high temperature with a two-side unit cell where it's the crystal lattice that imprints the potential. So here, think of this as our delta, just, you know, the distortion here, for example, of these ligand surroundings. And then the question is, can we have a true interaction-induced altomagnet? Okay? And so then the point is we want to start with a fully symmetric lattice, and then have also a Hamiltonian that fulfills, for example, here the four crystal symmetries. And then the point is, what I'll tell you in the next few slides, is that we can use another type of symmetry breaking, namely here it will be in forms of orbital ordering that can appear spontaneously from interaction, and then combine this with our Néel state, and that will give us the altomagnetic symmetries. And the way that works is we really just cooked up a elementary simple model, and the idea is that you start with, you know, two orbitals, an xz and yz orbitals, or, you know, px or py orbital, and here we chose this minimal model that was put forward for iron-based superconductors. And the whole model is actually invariant under C4 rotations here, because you also rotate the orbitals. And then we write down interactions that give us basically the Néel state, and then also here we have this interaction that induces the orbital ordering state. Okay? And so then you can treat that model, well, either with some more elaborate numerical method, or we can just do Hartree-Fock. And then you see that if you here have our term that's just a spin exchange that gives us antiferromagnetism, this here is this Ising type of interaction that gives us antiferroic orbital ordering. And it's in this coexistence regime where you get basically all the altomagnetic symmetries and then also the large spin splitting. Okay, and so this is now purely interaction induced here. Now, you already see that this is different from the Pomeranchuk, where this is really one transition. Here, these are two orders which are actually also competing orders, but nevertheless in the coexistence regime, you actually get all the symmetry requirements that you need here. Good.
Typically, this arrangement is ferromagnetic.
I'll come to that as my next slide. Okay, good. So you can ask like, okay, that's a nice toy model and so on. So where does that actually appear? So it turns out that in iron-based superconductors, that's basically how I came across this, because, you know, when I did my diploma in 2009, 2010, I was reading these papers about from Maria Daghofer, and, you know, they have papers where they have entire big tables of pictures actually of all possible magnetic and orbital ordered states. And if you look at this state here, that's exactly, that's from their 2010 paper. That's exactly the state that we propose. The state that is actually realizes this one here, this is the pi-0 stripe magnetism that always then induces the also orbital ordering. And the orbital ordering is, you know, as a precursor, the same thing of what was the nematic state that can persist even above the magnetic ordering. But when they do numerics and so on, it's never realized, and the reason is that it violates the good enough Kanamori rules, which just doesn't want to have both orbital and spin staggered. Good. So then you can look in the literature and you can violate the good enough Kanamori rules if you have strong quantum fluctuations in the orbital sector. And this was pointed out by Gignat, also by now a few years back. And in particular has been revisited in a recent work by also Jaron, where now the point is that if we just take the simple two orbital model, XZ and YZ orbitals, for realistic interactions, you might have seen that we basically we wrote down an interaction that gives us the orbital ordering. But for a realistic interaction, you just don't get it. But the trick is the following, that you know, instead of looking at this vanadate here, there's a second candidate, which is this chromate, that is in this nice paper from Gencano put forward. And the idea is you have to treat the full T2G manifold of the d orbitals, where you not only concentrate on the directional dependent XZ, YZ, but you also have to take the XY orbital into account. And then in the simplest picture, you basically can just have standard kinetic exchange that gives you an antiferromagnetic ordering on the XY orbital. And then, you know, the orbital ordering between the YZ and XZ is just coming from the remaining interaction, and this antiferromagnetism leaks also into these orbitals. Okay, and so in these systems, you know, there is actually a way of getting around this, and so there are certain materials there. There's a little twist here, so they call this. I'm not sure whether the nomenclature is very helpful. They call a slight problem that appears. Anti-alter magnetism, namely that if you go from one 2D layer to the other, the spin flips and it's fully compensated. So if you want to see spin splitting, you need to do it layer resolved, otherwise you don't see it. Or you can just look at the surface, and then at the surface termination you will get surface alter magnetism. And you know, this phenomenon they call anti-alter magnetism, but I think there are other contenders for anti-alter magnetism of different types as well. Okay, but these things happened also in these systems. Okay, good. So the upshot is there is a different mechanism, so you don't just need to look into materials databases for low symmetry crystals. It can also happen in these correlated systems spontaneously. Good. So then shortly after we did our work, and then we also realized that there's even a simpler state. And this is a work from Massimo Capone from Trieste. And they pointed out that if you just take a Hubbard interaction and then you go to very particular fillings, you have Van Hove singularities in the band structure. And then you can also have something like a compensated ferromagnet, where you just have a Q equal to 0 state, where just the XY orbital is basically polarized in one direction, and the XZ orbital is polarized in the other direction. And so that is also an alter magnet. Okay, but it's now Q equal to 0. But it's really, again, hard to stabilize in a proper itinerant microscopic model. But it tells you already that something interesting can happen. And, you know, we then moved on. And since we have worked on amorphous magnets, we were thinking like, you know, the whole discussion of alter magnetism is about crystal symmetries. And we've seen a lot of this. But then the question was, you know, do we need crystal symmetries at all? Or, we had worked on amorphous magnets. The question is, can we, for example, have something like this in an amorphous magnet? And that is difficult. And the reason is that there are gazillions of amorphous magnets. You take your favorite magnet and you just grow it too quickly and it becomes amorphous. And usually, there's lots of systems which are ferromagnetic, but if you want antiferromagnetism, you realize that you can't get like a bipartite structure in the system, so you usually end up with spin glasses, okay? But some of this wisdom that you also find in books does not necessarily need to be true, and we worked on, some exotic spin liquid that can actually form in these amorphous systems. But then if you have a Q equal to 0, alta magnet, you might actually think also, let's think about slightly different real space rotations. So we've seen the standard real space rotation where we take the whole crystal and rotate it, but we can also just think of our orbital space and just rotate the orbitals independently from that. So instead of having like something like spin space groups, if you want, there's a spin orbital space group. I think unphysically you not only switch off spin-orbit coupling, but let's switch off also crystal field effects if you want. Okay, and so then we can think of these orbital rotations independently, and then we can just ask, can we write down a toy model where we have full symmetry in spin space and orbital space that we can break spontaneously?
Can I ask
yes.
a question? In alta magnet, you have these nodal directions and anisotropy, which is a kind of feature, alta magnetic feature, and in an experiment we use it to say whether it's alta magnet or not. Here it looks everything is isotropic, so
we will see. We will break that spontaneously.
Oh,
That will appear spontaneously. Yeah. So just like you take a Heisenberg, let's say antiferromagnet, you start completely symmetric, but then it spontaneously chooses direction. In reality, there's always some single ion anisotropy and so on, and that chooses it. So what we do is we just write down a Kugel-Komsky model. People have worked on this, for ages. And then the idea is really it's a Heisenberg type in spin space and orbital space. So you have full symmetry in the systems. And then you already see what happens is that, if the orbitals are aligned here, you get a ferromagnetic spin interaction. If they are anti-aligned here between these two, you get an antiferromagnetic interaction. So you can now break spontaneously both the symmetry in the spin and orbital sector, and then that basically should remind you of something we've also seen, which is called atomic alta magnetism. So now here, since if you want, we think in terms of tight binding like models, we have basically the orbital degrees of freedom that encode the density, or in our case that would be then appear in the basically Hoppegan integrals. But here basically this is nothing but a d-wave spin density that we've now written into this orbital ordering. Okay, and so this can also be Q equal to 0, and so that is very much related to what Libor and Jairo and so have done in atomic alta magnetism. But of course, with a much more detailed symmetry analysis and so on. So this is really a toy model here. Good, and so then you can basically again do Hartree-Fock, which now becomes a bit more technical because you can't use translation invariance, so it's a bit of a beast. But the nice thing is you really find that you get spontaneous symmetry breaking for a large regime where now the orbitals choose spontaneously a direction that fix your nodal planes, and the direction of the moment is also chosen spontaneously and so on. Okay. Oh, the whole lattice structure, the whole crystal structure. Yeah.
Sorry, how do you physically avoid the spin glass in this case?
Oh, yes. So the spin glass we do avoid because we have 2 orbitals per side and so on. And so there is no frustration. So if you want, it's like a hidden ferromagnet. So the spin glass would come basically from a frustration if you have like a antiferromagnetic interaction. But we relieve that by basically having a ferromagnet on one of the XZ, or one orbital direction, and a ferromagnet in the other orbital direction. And the only other interaction that would frustrate you, they are basically chosen such that locally you always basically have the antiferromagnetic only locally arranged. So it's really the fact that we start with a Q equal to 0 order. It doesn't know about geometric frustration.
No, I understand that, but you're still dealing with spin ordering in the end of the day. Yeah. Even though it's Q equal to 0, I agree with you. In fact, an alta magnet doesn't have symmetry, okay? Yeah.
Is there actually spin order here or not?
Oh, there is actually spin ordering, yeah.
Right.
Yeah.
the
So what
question-
we've basically managed, I mean, it's a bit of a proof of principle. So essentially, in terms of like magnetism, it's not much more exotic than basically gluing two amorphous magnets together and just basically putting them locally in orbital degrees of freedom, which have a directional dependence. And that basically gives us the altomagnet. But there is no frustrate. If we would really put like a nearest neighbor proper, exchange, that would frustrate it completely, yeah. So what we are not saying is that you should take your favorite altomagnetic material and just grow it badly, have an amorphous system, and it becomes also an amorphous altomagnet. Which is, it's not so people are actually doing that. So I heard like in Berkeley, there are people who are growing these systems and looking at that. Well, yeah, Valentin knows more about this, yeah.
Well, maybe I'm really dim, but so on each side you have two arrows, one up and down, right?
That's
so
the spin.
yeah, but there's no net magnetic moment on site.
Correct.
Right. Okay. So it's a kind of it's ordered.
Yes.
But it's not a proper.
That's why I would call it
yeah.
a hidden ferromagnet.
Yeah, it's a hidden. Okay, I
Yeah.
understand.
Zero, yeah.
No, it's okay. But just to clarify, at this stage in the model, both the direction of the nodal planes and the direction of the spin are choice of the spontaneous symmetry breaking. So
Precisely.
they are fully unpinned.
Precisely. Yes.
Okay.
Yeah.
No, essentially, this is the ferroic behavior of altermagnets. That is the D wave, the higher order D wave ordering, or in this case, D wave that is ordering spontaneously, which is the dipole doesn't break. The dipole order in the L order doesn't break time reversal symmetry. Is this one? So you're having the pure amorphous, or exactly this idea of atomic altermagnetism.
Or think of your atomic altomagnet, but you have basically switched the crystal fields that would fix basically the D wave direction to zero, and it's just interaction that choose that spontaneously. That's it.
Why the spin is why the spin is assigned to yellow or red orbital? Why there is no superposition? The states should be degenerate if in energy if it's an altomagnet. No, so this yellow and red states are they degenerate
The yellow and red state. What do you mean degenerate?
in energy? So
There's two different orbitals. I mean, that's a new degree of freedom that we have.
Yeah, but why there is no states which are superposition? Because
Oh,
your
you
rules is
could.
operate.
Oh, yeah, of course. No, here we choose a direction, which is sigma z and tau z. You can choose here a tau x, which would look like a superposition.
Yeah, but then you lose these altomagnetic.
Then you would lose some of the systems. But if we have chosen the hoppings, well, okay. So this is now details, yeah. So if you basically chosen the hoppings also to be fully symmetric, then it's true. Then it's a bit accidental when you choose that, yeah. Now, in principle, there is a kinetic energy, okay, and that might, for example, turn the interaction as Heisenberg-like. But if the hopping itself has an Ising-like anisotropy, then we always end up with this one. Yeah. I'm not going to get.
All right. So sorry, how do you get around Hund's rules here? I mean, you've tuned that away.
Oh
but-
yeah, we get around Hund. This is a cheap answer. We get around Hund's rule, but just looking at this Kugelkomsky. We are not asking about microscopics. It's a proof of principle. Okay. Yeah. Okay. Yeah. Okay, good. So then you can do, let me skip over this. You can look at ARPIS and so on. Let me just point out you get nice spin splitting in the long wavelength limit that becomes sharp. You can even do cool things and look at spin splitter transport and you see what you get. But I want to still tell you a few other things because we've already seen a lot about the Lieb lattice and anti-Lieb lattices and so on. And of course, when we look at Lieb lattices, we've heard a lot that one might want to think about cuprates. And the Emery model, which comes here, because I know it's called the three-band Emery model, is equal to the Lieb lattice, is equal to the checkerboard lattice for delta equal to 1. Good, so they're all related and they all share the same symmetries and so on. Now, usually we always think about the Hubbard interaction on the copper, but there's also an interaction on the oxygens. And then we came across these papers, which were written well before I did physics. And this was about this intra-unit cell, possibility of intra-unit cell magnetism in the coppers. I'll finish that and then...
I'll give you why this has been falsified already. Okay?
Yeah, let me finish and then we hear why it has been falsified, okay?
Yes.
Good. So if you look in these papers, it's quite interesting. They have this, intra-unit cell peak, which onsets in the pseudogap. And then in the paper, they basically write pictures of altamagnets. And they have two candidates. The one is a loop current, and the other one is this one with magnetic moments on the oxygen. And that is the altamagnet that we had before. And now we hear where it has been falsified.
Okay, the problem is that there is extensive, high-quality oxygen NMR, and it says no magnetic ordering, no moment, in fact, whatsoever. So, in fact, my paper that I mentioned yesterday of 2008 was based on exploring what other possibilities there would be. But experimentally, we know that there is no magnetic moment on the oxygens. And so, from NMR, and that essentially says that this is ruled out.
Okay. Yeah. No. I mean, obviously.
The same is true for the Varma loops.
Yeah, but you have the same symmetry, would generate the same thing, and so on. Yeah. Okay, but it's quite interesting, that people were doing that at the time. And so then one question we asked, hypothetically, what would be a regime where we could get basically an oxygen moment? Okay, so what would we need to do to the microscopic to move into a regime where this could be true? And what you essentially see that the standard way of having our copper antiferromagnet is this: you get the band fogging, the pockets. If you go down and would induce also a weak moment on the oxygens, you just see that your pockets are now just spin split. And then you also can have this Q equal to 0 state where you only have moments on the oxygens, and then you get these large Fermi surfaces which are spin split, and that's exactly what you refer to as the nematic spin nematic state. And you have worked, or Eduard, but then there's also this actually nice paper by Una Kim and Mark Fisher, who also did some microscopics for that. Now, we just wanted to revisit that problem together with our collaborators and Rosa Valenti and Christoph Wohlfeld and postdoc and Valentin, who you all know. And just ask, if we take a realistic Emery model, we do not only mean field, but we also do exact diagonalization on the full clusters, including the oxygens. And then you ask where you are, and you see that, if you just look at the standard way, you would need a large kinetic exchange, which is mediated by a large UP on the oxygen. But the interesting bit is also that even the TPD, so a super exchange which is over the copper, can actually give you. So here the color coding is that this is the standard antiferromagnet, and then the blue one is the Q equal to 0 altamagnet, and the orange one is the pi-pi altamagnet. And the upshot is that for realistic parameters, probably you don't see it. But it's not that you're off by a factor of 10. Sometimes you are in the phase diagram, maybe 50% off. And then it's really just a question. You can go to higher doping. You can change basically the transfer energy on the oxygens. And it's not impossible. Okay?
TPP also?
Yeah, TPP is there. I mean, that's the easiest. If you take TPP large, TPP squared over UP gives you directly this. But this is actually not the leading term. The bit interesting thing coming out from cell perturbation theory is that TPD can also, increasing that, so you see increasing TPD also increases here the region for that as well. Yeah. So that's the bit, yeah. So don't know. Yeah. But I don't know. Do you know, Valentin? No. No. Yeah. But it's a good question, yeah. So we should basically go back and look at these anti-leap lattice, and because we have the whole, it's in the model. We just need to change it, yeah. Good. So then you can also think a bit of how to maybe get this in a material, and then Ying Li and Rosa, they basically also came up with a material where you actually would get oxygen moments. But again, it's not something that we want to say happens in every cuprate, but it's not too far away from what can be realized there. All right, and then we come back to this loop current question, because there was the other interesting bit. And you know, there's a whole zoo of that. And I just learned here in this conference that there's even a paper from 2016. There are many others, but they claim that they classify all possible loop currents also on the leaplet or in the Emery model from Matthias Scheurer. And then you basically can ask the question, now, can I also use loop currents to induce altomagnetism? And let's go away from the cube rates. Let's just say, as a proof of principle, can I basically use that here to induce altomagnetism? Or in the connection to orbital ordering, can this be the other symmetry breaking transition that basically lowers the crystal symmetry such that we get an altomagnet? Good. You have to be a bit careful because, you know, they are time reversal odd. So if you know, even something that looks like it has like, you know, these D-wave symmetries, because it's time reversal odd, can still be an antiferromagnet. But fortunately, there are many other loop currents. So a pattern like this, for example, you can then do your symmetry analysis, and then you realize that after you do translation and time reversal, you need another rotation to actually come back to the same state. So if we now don't have magnetism here, this is what we have seen several times in this conference, which is an orbital flux pattern with altomagnetic symmetries. Okay? And so in the previous talks, for example, by Raphael and also by Matthias Scheurer, you've seen that then you still don't get spin splitting. You always need spin-orbit coupling to actually see the spin polarization of the bands. Now the new message here is that if we now take these states and put just simple Néel ordering of that, then the coexistence of standard Néel ordering with these flux patterns, either here on the single side or here on something like an Emery type system, you still get then the spin splitting out of that. Okay, so you can have the coexistence again of two orders. It's again interaction induced, even though we don't really know the interaction for the loop currents. But you would have the same thing, that we can basically the coexistence of two orders giving us an altomagnetic state. Okay. Okay, good. So that's the main part. How many more minutes I have? Okay, so the final parts of the talk is about something that is a little bit more exotic. Okay, and so this goes under the name of fractionalized altomagnets. Okay, so that's a bit maybe an outlier in this conference, but normally I work on spin liquids, and you can ask the questions, and we're not the only ones doing that. Namely, can there be something like altomagnetic symmetries also coexistent with topological order? The only other community where I've seen so many group theory tables as in the altomagnetic community is if you go to spin liquids, where people do projective symmetry group classifications, and they love to write down huge tables and so on. So they can definitely compete with this community. So the question is, you know, can we have really what you know, some people would call an altomagnet star? Okay. And we don't want to just write down states on a mean field level. We really want to have like a proper proof of principle of that. And so we consider an exactly solvable model here. And so this is this picture, which is on the square lattice. And it's again related to these Kugel-Komsky models. But it now turns out to be exactly solvable Kugel-Komsky model, which has like for the spins an XY interaction. So there is a U1 symmetry in the system. And then we have like, again, two or we have new orbital degrees of freedom here, which you can think of, you know, they also, you can write in terms of Pauli operators. And now we put them in this vector, and there's also an identity here, and you know, each entry in this vector corresponds to the colors in these pictures. And now you have bond-dependent interactions here. And so in fact, this model is related to the celebrated Kitaev honeycomb model, where you also have these bond-dependent interactions. Good. So then the way you solve that is you just have an exact mapping. So instead of Holstein-Primakov, which you probably all know, you just map the spin to here, these fermionic representations. So you have 6 fermions that you need to introduce. We then take, you know, 2 of these fermions here, or these are Majorana fermions. We can build 1 complex fermion out of that. And if you do that mapping, it takes, you know, a bit of algebra, but it's really simple. You just basically can rewrite exactly that Hamiltonian. And now you see that you have these Z2 gauge fields appearing, which is just the redundant degrees of freedom, which turned out to be completely static. They are constants of motion, and they just basically set the sign structure of this hopping problem. And so now what you have is just some now fermions hopping on a square lattice, and then some sign structure, and then you can basically ask what's the lowest state, and it turns out to be the one with the pi flux. And now the excitations in your model, and the beauty why we choose that model, it's really exact. You don't invent anything. You start with a simple Kugel-Komsky, but we now know that the spins and orbitals, they fractalize into what we call fluxes. That's just locally changing the Wilson loop operator of these link variables here from 0 to pi. And then the rest of the spins here, they basically have 2 Dirac cones. And the Dirac cones, they come in 2 valleys here, which are related by translation symmetry. And now the interesting thing is that if you want to analyze the symmetries that you need to understand your ultramagnetic symmetries, you need to take care of this projective implementation. And how does that go? No, before I want to do that, I want to first put magnetism in the game, sorry. So the first thing is we take our model and we somehow spoil exact solubility, but in a very controlled way by putting an SZ-SZ interaction, which here just translates into a nearest neighbor repulsion of my fermions. But the crucial thing is still commutes with these link variables, so the Wison sector is still completely gapped and conserved and so on. And then what you get is basically just a gap opening for your Dirac fermions. And now this just looks like a charge density wave, and it is a charge density wave. But the key thing is that the charge density wave here corresponds to an easing antiferromagnet. So that is the simple one that is now what we call an easing antiferromagnet star. Okay? And now we want to imprint on that the ultramagnetic symmetries. And here you have to now worry that if you want to start with like the ground state, you have to choose a particular gauge. So here the purple ones are -1. So if I do a translation and this whole state is, the physical state is invariant under this translation, then you see that I end up in a different gauge. So you have to now supplement this physical implementation of a translation by a gauge transformation, okay? And that's how symmetries are implemented. And this you have to keep in mind when you now want to do your symmetry analysis. And in particular, you can think how spin flip and also time reversal are implemented. And since the spin flip is basically, so the spin is the orbital, the occupation of the fermions, you actually see that it involves a particle-hole transformation. And now you can then also write this in momentum space and see what this does for the band structure. So a translation brings us from one valley to the other valley, and a time reversal here now is a particle-hole transformation where I go from a up particle state to a Hall state. And so that directly implies that all my bands, so time reversal symmetry here implies that I have particle-hole symmetry in the system. And now if you analyze what that means for this state with magnetic order, it means that this upper bands, all the bands, they are not degenerate. Yeah? So the normal spin degeneracy of our simple antiferromagnet now translates into the degeneracy of the particle and Hall bands in different valleys. And that's important because now if we want to implement ultramagnetic symmetries, we can then go to some low energy effective Hamiltonian. So this is our normal Néel parameter here for the easing antiferromagnet. And then we can basically work out the microscopics of this term here that directly breaks all the symmetries but preserves a combined translation and rotation symmetry. And then what that means is that now my bands distort, but now what you should see here is that now my particle and Hall bands, so the particle and Hall bands here in the different valleys, they are now related by 90-degree rotations. Okay, and so the point is that instead of thinking that I have like a spin degenerate band, which is then split in a D-wave fashion, I now have basically degeneracy for particle and Hall bands, and they now split in a D-wave fashion that I need to relate them by 90-degree rotation. Okay, and so that's how you projectively can implement ultramagnetic symmetries, and that is really what you would call an ultramagnet star.
Where does the Fermi come from, the ultramagnetic?
This one here? Yeah, good question. So it is actually just a staggered, think of the checkerboard one. So now we have a staggered further neighbor interaction that breaks really the symmetry between these ones. Now the honest truth is, here we expanded around the low energy Dirac cones. Then you can actually write down an exactly solvable term. And we did that because just as a proof of principle, we wanted to show that it works. It's in the supplementary material because it looks a bit ugly. It involves, lots and lots of spin operators and lots of orbital operators. Yeah. So you can basically construct it, but it's not pretty. But this is only because you want to keep solubility. If you just basically lower the symmetry via some checkerboard next nearest neighbor interaction, you will also get it basically, but then it's not soluble anymore. Okay, yeah, a good question. Okay, so the answer is that there is something, and there is even something interesting in terms of symmetry classification, because now the ultramagnetic symmetries have to be taken together with your projective symmetries. Okay, good. And so that's all the stories that I wanted to tell you, and then not only thank you, but thank all the collaborators. Let me highlight in particular Valentin, who many of you know, who is here, with whom we started this whole endeavor of working in ultramagnets and thinking about non-trivial interaction effects. And then also in this final part here, there's Avedas Ni, who is a PhD student, and Urban Seifert. He has been really instrumental in this. And then there are, the usual suspects, and people like Alex Mork and Libor and Rosa, with whom we've enjoyed, discussing and working over the last years. And thank you. Yeah.
Do we have more questions? So I like a lot that you have extended the concept into several different fields with exciting models. Are in these fields any particular advantages of realizing the ultramagnetic states over antiferromagnetic, or
Advantages?
Yes.
Okay. Well, advantages. Well, for achieving what? I think this is I think a good spintronics question, because there is the point that you want to see that to do something with it. I'm not sure if you think of cold atoms, they want to realize that to understand it and so on. I'm not sure whether they really want to claim that once they realize superconductivity in the Hubbard model, on the doped Hubbard model. I don't think you do something. We don't build something with this superconductor. Yeah? So in the same vein here, I'm not sure whether there is an advantage for doing something technologically or something like this. What I think is there that one could do lots of probes and realize states which are not easily done in material system. Yeah? So for example, one thing which we've slightly touched upon is that if you take an ultramagnet and on top of that D-wave splitting, for example, think of superconductivity, you have lots of pair density waves, you have lots of exotic states that can come. If you have a more controlled way of implementing that, then I think that in principle would be a really nice test bed for looking at exotic forms of superconductivity and so on, which in real worlds, would be harder to realize, but we have the problem that they can't go to low temperatures. Yeah. The other thing is different probes. You can do these real space probes. You have like local resolution, all these kind of things, which you can't really do. Or you can do quenches, you can prepare states, things like that. But in terms of advantages, or like, for example, in terms of spin liquids, would this spin liquid be somewhat more robust against, destroying the topological order? The answer is very likely not. Yeah, no. So true. I mean, at this point, it's really just proof of principle things. Is it possible in principle? And the answer is yes. Yeah.
But I think it will help those conditions also enrich a little bit.
Yes. Yeah.
Not for any practical purposes, but
Yeah.
for actually spin liquid community that they haven't found one yet.
Exactly. Or, they love also to classify things and so on. So here, basically have a whole new set of classifications of ultramagnetic spin liquids of different types and so on. Yeah. But advantages in terms of some application type of thing, maybe I'm the wrong person to answer that. Yeah.
Thanks a lot. And if I may, second question to the last part. So how exact is the analogy with the spin groups in the magnets? So for instance, do you have there also some spin-only symmetry which is continuous in the Hamiltonian?
Yes. So you can really directly translate that. So there should be a way of directly doing the spin. But the point is, you have to then just for a given gauge ask how it's microscopically implemented, and how would you basically then find a state that is invariant under the physical implementation, but in a fixed gauge. And so this is essentially, but I think you can essentially take all the usual projective symmetry groups and then analyze them in terms of spin groups as well.
So you don't need another long table. You can just.
I think you can marry the long tables. Yeah.
Thanks.
Yeah, thanks for the nice talk. Can you you said the gauge field that you get is not dynamic, right? But I think one of your slides had deconfined on it. It's like, what did you mean?
Well, deconfined basically means we choose a model where the gauge field is not dynamic, it's soluble, which means the fermions are always deconfined. Yeah.
Okay, but you cannot go, you don't have a confinement-deconfinement phase transition in there as well.
Well, not in the model that we have. If you now don't fine-tune your interactions, but just write down a generic, let's say Heisenberg or whatever interaction, then there will be a transition to a magnetically ordered state, which will be a confinement transition.
Okay. And in principle, you could do the symmetry breaking game also with a different spin liquid, like a U1 or...
Well, so that is, so one of the things which is maybe more related to the question. So one of the famous models in spin liquid research is like a J1, J2 model on the square lattice, okay? And so you now can ask, and there is an intermediate regime where people believe, and for decades, people have fought over around the frustration point J2 over J1 square root of 2, whether there's a spin liquid. And there's a big spin disordered region around it, and people believe there might even be like a Dirac spin liquid there. So now you can ask what... Well, it's now the latest ones, I don't know, is that it's a Dirac Z2 spin liquid. You can have a Dirac spin liquid Z2. We can have a gapless Z2 spin liquid. The Weisons are gapped, but the fermions can be gapless. The Kitaev honeycomb model at the isotropic point is gapless, but it's Z2. And so the point is, you can ask what happens if I now stagger that in the checkerboard fashion. And so one interesting idea would be, can there in not soluble models but more generic system, is there a proper altomagnetic spin liquid and so on, yeah? Which I don't know, I don't know whether it's more robust against the ordered states and so on, yeah. Maybe now thinking about it, maybe there is something. I don't know, yeah.
Thank you.
Yeah.
So regarding the first part, when you had the distorted lattice, it looked like the symmetry of the outer magnet came from the orbital symmetry, not from the lattice. Yeah. What's the role of the lattice symmetries in all of it? Like, can you have some interplay or?
So yes, you can. So in like what we call the pi-pi altamagnet, then we do marry basically the orbital directional dependence with the translational symmetry breaking of the lattice itself and so on. Yeah? So you can think of different types of orbital order, and there will be an interplay of, on how you break lattice symmetries and how you on top of that break orbital symmetries. Now the point is, if you have the q equal to 0, 1, that is not necessary there. But in principle, you have a whole rich structure of also intertwining the lattice symmetries with the orbital symmetries itself. Yeah.
Okay, if there are no more questions, then it's coffee break. Let's thank the speaker one more time.